Okay, so in this example, we've got a wire with current flowing inwards. That is, the wire is pointing in the inwards outwards direction, and we specifically know we have current flowing inwards. And I think we're going to treat that as the source that's influencing everything else. And in particular, we have this source current is going to, how would we determine the direction of the magnetic field that it creates?
Right-hand rules, number one.
Yeah. So what would be one variation? What would be a variation of that we could use to find the direction of the magnetic field here? Or what would the magnetic field look like? If this wire is the only thing creating a magnetic field, what would the magnetic field nearby look like?
I used the right-hand rule where I had my thumb pointing into the page, and when I curled my fingers, ended up getting the magnetic field curling to the right.
What do you mean by to the right?
Oh,
because in general, we should expect a magnetic field caused by a loop of wire to form sort of loops around that loop or sorry, a straight wire. We should expect concentric circular loops.
mm-hmm.
But how would we would probably describe the direction as either clockwise or counterclockwise.
Oh,
so which one of those makes sense here?
I got clockwise for this one.
Yeah, if you point your thumb in the inwards to the board direction, the curl of your fingers suggests clockwise. So that means we have clockwise magnetic field. That doesn't mean anything's moving in the clockwise direction. This is just the direction of the magnetic field vectors in this region of space. So that's the magnetic field, what the magnetic field lines would look like in the region around the wire. And if we care about the effect this has on a particular test object, like let's say, for example, this -3Q charge over here. At this location, what's the direction of the magnetic field caused by the source current?
Is it pointing up?
Yeah, it should be straight up. And one way to check, if you're not sure, a useful thing to keep in mind is that the magnetic field is always going to be perpendicular to the current that created it. Or if it's created by a moving charge, it will be perpendicular to the velocity of that moving source charge. And magnetic field is always perpendicular to the radius. Radius in the sense of the straight line vector from the source out to the location of interest. So if we were to draw a radius vector here, a radius vector is just from the source charge, or in this case, the source wire, out to the location of interest. So we have an inwards pointing vector and a leftwards pointing vector. Those two vectors, inward and leftward, form a plane. What are the only possible directions perpendicular to that plane? That is perpendicular to leftward and perpendicular to inward.
Up or down?
Right. So that means at this location, before we even apply any right-hand rules, at this location, we can narrow it down to upwards or downwards being the only possible directions of magnetic field. So we know the magnetic field at this location must be upwards or downwards from those perpendicular properties. And then we can use any variation of the first right-hand rule to choose one of those two. But you can always narrow it down to two possibilities before you even apply any right-hand rule. The same is true for torque, by the way. Torque is always perpendicular to the moment arm and perpendicular to the force. So you can always narrow it down to two possible directions for torque and then apply a right-hand rule to choose one of those two. That's ultimately going to be the case for any right-hand rule. So right-hand rule looks like it suggests upwards, either by using the point your thumb in the direction of the current and curl your fingers, and the curl of your fingers tells you clockwise or counterclockwise. Alternatively, you could put your hand at the location of interest, stretch out your fingers straight towards the source, and curl your fingers in the direction of current, and your thumb will tell you the direction of the magnetic field. In this case, that definitely looks like it is upwards. So we got an upwards magnetic field at this location.
Could you say that again, Casey? I'm sorry. The last
right-hand
rule.
rule. Yeah, one way, and this is a variant on the first right-hand rule that's specifically if you only care about the magnetic field at one location. Put your right hand at the location of the location you care about. Stretch out your fingers towards the source, and notice you can still swivel your hand around. And you want to curl your fingers in the direction the current is flowing, or the direction the source charge is moving. And your thumb will tell you the direction of the magnetic field at that one location.
Okay, thank you.
Any other questions on the direction of the magnetic field so far? And in general, the first right-hand rule or any variation on the first right-hand rule is all about the relationship between the source current or moving source charge and the magnetic field it creates. But now that we've got that, the source current creating a magnetic field, from this point onward, we can ignore the source current and just say the magnetic field can exert a force on the moving test charge. And for that, we would use the second right-hand rule. We've got a moving test charge in the presence of a magnetic field. So we should expect it to experience a force, or at least possibly experience a force. And that also has some perpendicular properties we should consider. In general, the magnetic force is always perpendicular to the velocity of the test object. Or if you're talking about a force on a wire, perpendicular to the current in the wire. And the force is always perpendicular to the magnetic field itself. So in this case, you've got an upwards magnetic field and a rightwards velocity. What are the only two directions that are perpendicular to both of those?
Inwards or outward?
Yeah, so that means the force on this charged object has to be either straight into the page or straight out of the page. And then we can use any variation on the second right-hand rule to determine which one of those it is. And usually the three-finger variation of that seems to work best. You have your thumb in the direction of the velocity, the motion of the charge, index finger in the direction of the magnetic field, and your middle finger perpendicular to those will tell you the direction of the force. So which one is that in this case?
Out of the page.
Right, we get an outwards force except for one thing. What kind of charge is this?
It's a negative charge, so we have to flip it.
Yeah, a negative source, a negative test charge will feel the opposite effect. So you can use the right-hand rule as normal, but then just flip the final result. Or alternatively, you could treat a negative charge moving in one direction as if it were a positive charge moving in the other direction. If you pretend this negative charge moving to the right is actually a positive charge moving to the left, you could point your thumb to the left, then index finger upwards for the magnetic field, and your middle finger will tell you the actual direction of the force. Either way, it looks like that's going to be an inwards force, which we would typically draw as an inwards pointing arrow, an arrow pointing away from the viewer, a circle with an X in it. So that would be the force acting on this object. And what would that make it do, by the way? If you have an object that's moving and it experiences a force in a direction perpendicular to its own velocity, what does that do to the object's motion?
Is it slower down?
Not quite. If you want an object to slow down, which direction would the force have to be in relative to the velocity?
The opposite?
Yeah. So if you've got an object moving to the right, a force to the left will make it slow down. Or if you wanted to make it go faster, you'd have to apply a force in which direction?
The same direction.
Yeah. A force in the same direction it's already moving, same direction as the velocity will make it get faster. So opposite direction of velocity, a force will make it get slower. A force in the same direction as velocity makes it get faster. If it's perpendicular, though, that's not in the same direction or the opposite direction. It's something else entirely. So a force perpendicular to the velocity doesn't make it get faster, doesn't make it get slower. But how does it change the velocity?
And would it put a spin on it? are
Yeah,
rotated?
well, it's not exactly so much that it makes the object rotate, it's that it makes the path curve. So instead of the object traveling in a straight line, the object is going to curve in the direction of the force. So for instance, in this case, you've got an object traveling to the right, it's experiencing an inward force, so it's going to end up traveling inward and to the right. Not straight inwards, it still has its rightwards component, but it's now traveling to the rightwards and inwards. And in fact, since the magnetic force is always going to be perpendicular to the velocity, as we were talking about over here, since the magnetic force is always perpendicular to the velocity of the test object, that means the magnetic force is only going to change its direction of travel. It's not going to change its speed. So it's going to travel in a curved path. Eventually, if you have a constant magnetic field, curving along a circular path, but not changing how fast it's traveling. So in general, if you've got a charged particle moving in the presence of a constant magnetic field, it's going to travel in a circular path, or if it's on some diagonal, it might travel in sort of a helical path. But there's going to be some sort of curvature to its path of travel. Any questions on that so far? And let's take a look at the charge down here as well, this positive 2q charge. At this location, what would be the direction of the magnetic field? At this location below the wire. And it can't be downward because it's got to be perpendicular to the radius vector. Remember, the radius vector here is the straight line vector from the source to the location of interest. So we need the magnetic field is going to have to be perpendicular to that radius vector. It can't be left or right either, though, because, or wait, no, sorry, it has to be left or right. Yeah, you're right. I was looking at the wrong velocity vector. Yeah, the magnetic field has to be perpendicular to the radius vector and perpendicular to the current. Those form this plane here, up, down, and inwards, outwards. The only dimension left over is left and right. So at this location, the magnetic field has to be either left or right. And the right-hand rule chooses one of those. So of those, which one fits the right-hand rule based on this current?
To the left.
Yeah, it should be to the left. We can see that from the concentric circles we drew out earlier. Under the current, we have a leftwards trend. And you can also use the other variation on the first right-hand rule. Put your hand at the point of interest, stretch your fingers straight towards the source current, and swivel until you can curl your fingers in the direction of the source current. And your thumb will tell you the direction of the magnetic field at that location of interest. So in this case, that is definitely to the left. And now that we've got the magnetic field at this location, once again, we can ignore the source charge, or sorry, the source current. We can ignore the source current and just say the magnetic field itself is creating a force on the test object. And in this case, with the test object moving to the right and the magnetic field to the left, what does that tell us about the force on the test object?
Equals 0.
Yeah, no force at all because the magnetic field is parallel to the velocity. Right. The right-hand rule, the second right-hand rule doesn't really even apply here. You can't point your thumb in the direction of velocity and your index finger in the direction of magnetic field if they're parallel. They've got to have, they don't have to be perfectly perpendicular, they just have to have some perpendicular component. Like for example, if the velocity, let's say the velocity was to the right and the magnetic field was up and to the right. If we had a situation like this. In that case, there is going to be a force because the magnetic field and velocity are not parallel, but they're also not perpendicular. So you're not going to get as strong a force as you could. One way to handle that is to think of splitting the velocity up into components. You could say the velocity has a component parallel to the magnetic field, which doesn't do anything, and a component perpendicular to the magnetic field, that V perp there. So we could say that the magnetic force is the magnetic field times just the perpendicular component of the velocity. Or alternatively, we could keep the velocity and split up the magnetic field into components. We could say the magnetic field has a component parallel to the velocity and a component perpendicular to the velocity. So one way of handling this is we could say the magnetic force is charge times velocity times just the perpendicular component of the magnetic field. Or more commonly, we would just say the magnetic force is the charge times the magnetic field times the velocity times the sine of the angle between them. That's usually the way we would calculate that. But the sine of the angle between them ultimately is just taking the perpendicular component of one of them, just like torque does. Any other questions on that so far? And I think we can also see that by going back to the general formula for the force on the test on the point charge. What's the usual formula for that magnetic force?
QVB total.
Yeah, Q times V
Sine
times B times what was that?
sine theta, and theta is the angle between V and B.
Right, exactly. So if they're parallel, like in this case, if the velocity and the magnetic field are in exact opposite directions, what's the angle between two vectors in exact opposite directions?
180.
Yeah, and sine of 180 degrees is
0.
right. So in that case, it doesn't matter how much charge there is or how fast it's moving or how much the magnetic field is. Sine of 180 is 0. Sine of 0, if they're in the same direction, would also be 0. So in general, if the velocity is parallel to the magnetic field, you get no magnetic force at all. There might be other forces. Maybe there's an electric force, for instance, but there's no magnetic force. Any other questions on the magnetic forces or the right-hand rule so far? And what about at this location? We're at sort of a diagonal here. The radius vector would be this diagonal. So what are the only options for magnetic field at this location? That is, what would be perpendicular to the radius vector and perpendicular to the source current?
Is it west north? Northwest.
Yeah, northwest or southeast. And in particular, because of the curvature of the directionality of these curves, it should be directly to the northwest. So we can say that at this location, the magnetic field is directly to the northwest, 45-degree angle. And then what can we say about the magnetic force on this test charge as a result of that magnetic field?
Don't we need a velocity vector to know what is
Mhm.
the
Right. And if this charge is not moving at all, if its velocity is 0, what does that tell you? What happens to this equation if V is 0?
no magnetic?
There's no magnetic field.
force.
There is a magnetic field, but yeah, no magnetic.
Of course.
Yeah, exactly. That the magnetic field is created by the source wire, but a non-moving charge doesn't experience any force from that magnetic field. It could experience a force from an electric field. Presumably the other charges, if we treat them as source charges, would be creating electric field, which could exert a force on this. But a magnetic field only exerts forces on a charge if it's in motion. Current also counts as a moving charge. If we had a wire somewhere around here, like let's say, for instance, we place another wire in this region. Let's say at the location on the bottom, let's say we remove this 2Q charge here. And in its place, let's say we put another wire. Let's say specifically a wire that is straight up and down, that has current flowing upwards. So let's say we've got electrical current flowing upwards in this wire. Is that wire going to experience a force from the magnetic field caused by the other wire? Does this count as moving charge?
Can you repeat the question again?
Does this wire count as moving charge?
Yes, because the current is moving, like the
Mhm.
component in the current is moving.
Yeah, even though the wire itself is staying still, the fact that current is flowing means charge within the wire is moving. And what's physically going on is all the protons are staying still, but all the electrons, or many of the electrons, are moving downwards. But electrons moving downwards, negative charge moving downwards, can be treated as positive charge moving upwards. So we'd say current is flowing upwards. And that's moving charge in the presence of the magnetic field. So that should experience a force. And how would we decide on the direction of the force there? Can we apply the second right-hand rule here? Thumb generally points in direction of what here?
For velocity, but in this case, we can use the I direction, the
Yeah.
current direction.
Exactly. So that'll be upwards. The wire itself is not moving. It doesn't have a velocity. And in fact, even if the wire was moving, we wouldn't really care about its velocity. The important thing is current is flowing upwards within this wire, and current is by definition the motion of charge, the flow of charge. So we can see there's an upwards motion of charge. Then point your index finger in the direction of the magnetic field. Well, we're not treating this wire as a source charge. If we were treating the wire as a source charge, we could say its magnetic field is creating magnetic field in the counterclockwise when viewed from above direction, or clockwise when viewed from below, depending on your point of view. But since we're treating this as the test object, we don't care about the magnetic field it creates. We care about the magnetic force it experiences from something else, from, in this case, the source current. So we would use the second right-hand rule to determine the force that the test object feels. We've got current flowing upwards, magnetic field from something else pointing to the right. So the force would be in the outwards direction. So that means this wire experiences an outward force. The wire is presumably fixed in place somewhere though. So that's just going to mean that the wire bulges in the outwards direction. It's going to bend. But we would describe that as the wire itself experiencing a force in the outwards direction. Outwards, so we draw that as a circle with a dot. So that would be the force on the test wire as a result of the magnetic field created by the source wire.
Quick question, Casey. So current's always going to be, I mean, we're going to treat it as positive charge, right?
Yeah.
Okay.
The thing is, when we say current is flowing upwards, what's actually happening is electrons are moving downwards.
Correct.
We don't really care about what's actually going on within the wire. Negative charges moving downwards are effectively the same as positive charges moving upwards. So when we say current is moving in a certain direction, we can treat that as the direction that positive charge is moving, even though it's actually negative charge moving in the other direction. But for all practical purposes, current can be treated as the motion of positive charge. Any other questions on that so far? And one other thing to keep, one other thing about the current, the force on the wire here. Have you seen any formulas for the force that the wire would experience?
I don't think so.
We can actually make one by modifying the formula we've got for force on a source force on a single point. Because the force on a moving point charge, like just a single small object that's got charge and is moving, is charge times velocity, or charge times speed times magnetic field times sine of the angle. But we can modify that a little bit based on expanding, what exactly does speed mean? This V here, what's the definition of speed?
It's the velocity and direction, or like, yeah.
Well, other way around. Velocity is speed and also including direction. But what is
Correct.
speed
That's
mean?
what I meant.
Ignoring direction for the moment, what is speed? Like if I said the speed of this object is 5 meters per second, what information am I using to calculate that? Yeah, distance divided by time. So speed can be written as distance divided by time. And then we're multiplying that also by magnetic field and sine of the angle. But the thing is, dividing by time, we can take any of these things in the numerator. We can just treat this whole thing as the numerator divided by time. If we rearrange this a little bit, let's say I instead group together charge over time. What's charge divided by time? That is how much charge divided by how many seconds? What quantity is defined as amount of charge over amount of time? Think back to the circuit stuff in 7b. What were we defining as the flow rate of charge? How much charge flows past per second? Yeah, this is exactly the definition of current. When we say that like 5 amps of current are flowing in the wire, 5 amps means 5 coulombs of charge per second. Amps just means coulombs per second. And current is defined as charge over time, formerly delta charge over delta time, or the derivative of charge. But this quantity, charge over time, is current. So we can rewrite this force equation as force equals current times distance. And what distance actually matters for a wire? What distance are we talking about when we're talking about some wire? Is there any distance that's actually relevant for a wire?
Like the length of the wire?
Yeah, that distance is just the length of the wire. So current that's flowing in the wire times the length of the wire times the magnetic field, and then times sine of the angle. And in this case, that'll be the angle that the magnetic field makes with the wire itself. So if you got a wire and a magnetic field, the angle between the wire's direction and the magnetic field direction is the angle we're talking about here. So this gives us a formula for force that a wire would experience. A wire with current in the presence of a magnetic field from something else will feel a total force equal to the current flowing in the wire times the length of the wire times magnetic field times sine of the angle. And we often rewrite this by dividing both sides by length. So you could say force per unit of length. That is like force per centimeter, for instance, equals, and then all that's left on the other side would be current times magnetic field times sine of the angle. So we can write this as how much force, how many newtons of force we experience per meter of length of the wire. But either of these would apply to a wire. Because a wire with current will experience a force in the same way that a charge that's moving will experience a force. Any questions on that so far? So a charge object that's moving in the presence of a magnetic field can experience a force as long as the motion is not parallel to the magnetic field. A wire with current flowing in it in the presence of a magnetic field can experience a force, again, as long as the wire is not parallel to the magnetic field. What else? What's another object that can experience a force from a magnetic field? A magnetic field influences a moving charge. A magnetic field influences a wire with current. What's the other type of object that can be influenced by a magnetic field? Probably the kind we deal with much more often in everyday life. What do you usually use a magnetic field for? I mean, usually you're not using a magnetic field to move charges around or to push on wires. Usually, what do you use a magnetic field for in a more common application? What's a much more common everyday experience of magnetic forces? Yeah, a fridge magnet, just a permanent magnet, a bar magnet. So let's say we have one of those instead. Let's say instead of a moving charge or a wire with current, let's say at this location, let's say we just have a bar magnet. Which presumably has a end marked north and an end marked south. So this bar magnet counts as a magnetic dipole. Dipole just meaning it has two opposite ends, which we call the north end and the south end. If we place that in the presence of an existing magnetic field, in this case, pointing up and to the left, what's going to happen to this magnetic dipole in the presence of an existing magnetic field?
Will they create a total magnetic field?
The bar magnet creates its own magnetic field, but that would be if we're treating it as a source object. Let's say we're treating the bar magnet as a test object. So we don't care about the magnetic field it creates on its own right. We care about the effect it feels from somebody else's magnetic field. So we're just measuring what happens to this bar magnet, not what this magnet does to something else. Yeah, in general, if you have a dipole, whether it's a magnetic dipole in a magnetic field or an electric dipole in an electric field, a dipole will tend to align with the field of the same type. So the magnetic dipole, like a bar magnet, will experience a torque that pushes it towards aligning with the existing magnetic field. And it's often useful to draw the magnetic dipole moment there. The dipole moment is going to be a vector, in this case, for a bar magnet, the dipole moment is a vector pointing from the south end to the north end. And we usually call that M for dipole moment, for magnetic dipole moment. And this behaves very much like P, the electric dipole moment for an electric dipole. So this magnetic dipole moment is just describing, its direction is just describing the orientation of the bar magnet. Its magnitude is describing how strong of a bar magnet it is. But if the bar magnet is in the presence of a magnetic field from something else, some other source, the bar magnet is going to experience a torque that pushes it so that its magnetic dipole moment will align with the existing magnetic field. So if this is free to rotate, it's going to start to swivel until it lines up with the existing magnetic field. And then because of momentum, it will keep swiveling, but then it will snap back and it will just sort of oscillate, eventually losing energy due to friction until it aligns with the magnetic field. And this is ultimately how a compass works. The compass needle is just a small magnetic dipole, very lightweight, so that it easily swivels to align with the existing magnetic field. Any questions on that dipole stuff? And if we do want to treat the magnetic dipole as a source, we can say the bar magnet creates its own magnetic field. And let's see what that would look like. Let me clear out some more space here. So let's say we have just a bar magnet. With one end that we would describe as the north end of the magnet and one that we would describe as the south end of the magnet. First of all, what does it mean? Why would this lump of iron generate a magnetic field in the first place? What is it about this lump of iron that says charges are moving? Does this magnet contain any charges? I mean, this lump of metal? What charges would you find in any object? At the very small level, what's everything made of?
Electrons?
Atoms.
Ultimately atoms, yeah. And even smaller than atoms, what are the atoms made of?
Electrons, protons, and
Or
neutrons.
Right. And we don't really have to care about the neutrons because those are by name neutrally charged. But the protons and electrons have positive and negative charge. Note that that's not distributed to the north end and the south end. The north end does not have more charge of one type, and the south end does not have less charge of one type. The charges, protons and electrons, are evenly distributed. This object has the same number of protons as it has electrons, which is why it's not creating an electric field. But what are the protons doing versus what are the electrons doing? Where in the atom would you expect to find protons versus where are the electrons?
Electrons are in the periphery, like in
Mhm.
space, and then protons will be in the nucleus.
Yeah, the protons are all concentrated together in the nucleus, and the electrons are whizzing around in the electron cloud shells out on the edges. And most importantly, that means the protons are staying relatively still, but the electrons are in motion. That means the electrons are moving charge so they can create magnetic field. The protons are not moving, so they don't create their own magnetic field to cancel that out. However, the electron's magnetic field is essentially in a random direction. If you've just got a whole bunch of atoms packed together, each atom could have its own magnetic field caused by the motion of the electrons. But if you've got lots of atoms in just random orientations, their magnetic fields are pointing in every which way possible. And what would you expect to happen if you add together lots and lots and lots of vectors in random directions? If there's no overall trend, just a bunch of random directions of arrows. Yeah, if you just add together a bunch of arrows in random directions, you would expect them to mostly cancel out. So a typical lump of matter, like just this pen here, each atom could have, each electron can generate a magnetic field, but since there's no general orientation, there's no uniformity of orientation, that means they all cancel out. But in certain materials, such as iron and a few other metals, it's possible that if those all happen to be oriented in the same way, like if instead of a bunch of just random directions, if instead of just a bunch of random directions canceling out, let's say most of the atoms happen to be aligned in roughly the same direction, not even all in the same direction. If there's just overall a general trend towards mostly the same overall direction, then when you add those up, they form one big vector in that direction. So that means overall that object creates a magnetic field. That's the big idea of a bar magnet or a permanent magnet, a magnetic metal. It's a lump of metal where all of the magnetic fields of, not even all of the atoms, but enough of the atoms are oriented in the same alignment. And so their magnetic fields combine overall instead of mostly canceling out. So that means that this bar magnet creates a magnetic field. It's still caused by moving charge. It's just that the moving charges are these spinning electrons within the atoms. And what that magnetic field is going to look like turns out to be the same general shape we get from an electric dipole. You'd have field lines coming out of the north end, going into the south end, and sort of curving around. However, unlike the electric dipole, this is not caused by uneven distribution of charge. It's not like there are lots of north particles at one end and lots of south particles at one end. The north and south is really more about the direction that all of these atoms are aligned, or again, enough of these atoms are aligned. So the north end is just the side that most of the atoms are pointing towards in terms of their own magnetic field. And the south end is what most of them are pointing away from. So we'd expect the magnetic field caused by this dipole to look like this. However, if you take a look at what's going on inside, what would you expect to happen if you break a bar magnet? If you crack this in half, do you get a north piece and a south piece?
Wouldn't it make two magnets?
Yeah, you get two magnets. And yeah, each one would be a magnetic dipole. You'd have one piece that still has a north end and a south end, and another piece that also still has a north end and a south end. Because this is not about a piece that's called north that you're breaking off and a piece that's called south that you're breaking off. It's about the whole magnet, no matter how big or how small the pieces you cut it into. Each piece of that still has that alignment of individual atoms being oriented the same direction.
Would that make the magnetic field smaller for each magnet itself?
If you break it apart and separate them, then yes, the two
Okay.
pieces individually would have weaker magnetic field.
Yeah, okay.
But if you just make a slight cut here, but keep them in the same position, the whole thing overall still has that strong magnetic field. In fact, you can even see what's going on inside. If you take a look at what's going on within the bar magnet by, let's say you cut a hole in it and put a compass here, that region also has magnetic field going away from north and towards south. So something like this. And it turns out that you can see what's going on at any location inside the magnet. If you were to cut a small hole here, you get magnetic field continuing within the bar magnet. And in fact, it turns out that magnetic fields don't really start or end anywhere. Magnetic fields form complete loops. That is, the field lines keep going within the bar magnet, forming complete loops. So in general, a magnetic field line, just like the ones that form around current in a wire, magnetic field lines always form complete loops, except for ones that start at infinity and continue on to infinity. But all the other ones form complete loops with no beginning or end. And we generally describe that by saying there's no such thing as magnetic monopoles. There's magnetic dipoles with a north end and a south end. But you can't have like just a north particle that all the field lines are coming out of. You can't have just a south particle that all the field lines are going into. Magnetic field lines always form loops. Any other questions on that? All right, then I will see you next time.